All right, here we go. Momentum. Recording this lecture so that you can have it to hold forever. Should you need refresher on all this stuff, should you have maybe missed the whole first part of this week. Not anyone in particular, of course, obviously. Several guilty parties there. Anyway, all right, so momentum. This will be the notes for 3.5 and 3.6. We'll just leave it in your notebooks in 3.6, I think is probably the section you're on. But just make sure that this is somewhere. So let's go into momentum. We've spent 2 days tinkering with the blue carts and the gizmo thing yesterday, so that now today we can have hopefully a good productive discussion about momentum and do some actual math. Yay! All right, so momentum. Well, let's start at the beginning. What is it?
Mass of velocity.
Yes. I guess we should do the definition-ish kind of thing. So let's make it look official-ish. Well, hold on, we're going to get to that. Slow down. Let it breathe a little bit. So, to your point, thanks for jumping ahead. Is momentum a scalar or vector? Or is momentum a scalar or vector quantity? Well, to know this, we should probably define scalar or vector first, before we can decide which one it is, in case we didn't read ahead. What's a scalar quantity in physics? Give me an example of a scalar quantity in physics. Huh?
Speed.
Okay. I don't like gravity at all. No. No. Ooh. Sort of. Mass is a scalar quantity. There's others, to be sure. Why is mass a scalar quantity? Does not have a direction. Scalar quantities in physics are like magnitude type things. Mass is just a thing. You have some amount of mass, whatever that is. It doesn't have a direction. But what about something like velocity?
It has a direction.
It has a direction. Inherently, by definition, velocity has a direction. So if we're using two quantities, one of which is a scalar and one of which is a vector, to define momentum, what would you say momentum is then? Scalar or vector? Vector. So what does that mean? Yeah, so momentum simply has a direction. At the end of the day, once we get down to calculating it, momentum is also something that inherently, by definition, is going to have a direction attached to it, really because it has velocity attached to it. Right? So momentum can have a direction. Okay, Larimer, that sounds great. What's next? What did you explore in the Investigate yesterday, and what did you read about in the physics talk from yesterday?
Car crashes.
Okay, yeah, we were crashing things together.
We were seeing how, we were putting them together and they were going together.
What did you discover was always true? So this is a core, key, bedrock, fundamental principle of physics. The law of conservation of momentum. Now, in this class, we're going to use carts. We're going to talk about cars, objects, blocks, maybe even like a pool, like billiard balls. Like that's the stuff we're going to talk about. But we've found in physics that this law of conservation of momentum holds true for everything we've ever been able to experiment with, including like the super small stuff, like protons and neutrons and things in nuclear reactions and the Hadron Collider and all those sorts of things. Conservation of momentum is held pretty much everywhere that we've had a chance to check it out. It also seems to work for really big things, stuff like astronomical things and comets hitting planets and asteroids and things like that. Conservation of momentum has always been shown to be a thing. So what does conservation of momentum mean then? For us.
If you're conserving your momentum, it's the same before and after.
In a collision of objects, total momentum of objects before is
Is that only when, like, in the simulator, the elasticity was set to 0? Because if it's not, they would just bounce off and they're not combined, or is it still the same?
it's total is the key word here.
Total is the same.
Total is the same. Now, to your point, different directions, bouncing off, everything else, that's where we're going to get into the vector part of this, right? Because if I'm moving this way, I would have positive momentum. Something moving the other way would also have momentum, but as we consider them both, one would be negative. So yes, but this holds true regardless. And the key word here is total. That's why I underlined it. This is the sum of the momenta of the objects. Before, it's going to equal the sum of the momenta of the objects afterward. But the individual momentum of some given object can, and in most cases will, change. Right? So an object doesn't stay the same and have the same momentum, but the total momentum, when you consider all the objects and you add them all up, that is what is going to be the same.
So is negative momentum a thing? Like if it was going forward and then it hits the thing, then it gets launched backwards, would you consider that negative?
Yes.
momentum?
Forward would be positive, backward would be negative. Left might be negative and right would be positive or whatever, right? North would be positive and south would be negative. So to your point, yes, this is a directional quantity, so it can and will absolutely have a negative value.
So if the momentum is always the same, then if something bounces off but it still makes that move, do they split the momentum or do they both have that much?
That's where the math comes in. So to your point, sort of, right? Like there's going to be a reshuffling, let's say, of the total momentum into both of those objects. So depending on the kind of collision, which is what we're going to talk about next, yes.
If two objects are moving towards one another and one has like more momentum, or like more momentum, I guess.
Sure, yeah.
Then would both of them keep moving with the one that has more momentum?
So depending on the type of collision, maybe, right? Because we did two types of collisions. Day one this week, what kind of collision do we do? What did the carts do on the first day? It was elastic. What did they do? They bounced off each other, right? There was a spring and it just kind of bing and it went backwards. What were the collisions yesterday like? Stuck together. So those are the two types of collisions.
How is momentum explained in, like, explosions?
Oh. I don't know if we'll get to that today.
Was that in the book?
But guess what?
In the book, but like, it wasn't really explained very well.
It's still conserved.
Yeah, but like how does it define, because it's mass times velocity, there's no velocity, but there's a lot of mass, and velocity is.
Okay, so consider an explosion.
Yeah, there's a lot of. But like, is
If I
the
have,
energy-
if something isn't moving, okay, we would say how much momentum does that have?
Zero.
Zero. If something explodes in all directions, okay, and for the sake of all directions, let's just say it explodes left and right.
Yeah.
Would the momentum still be zero?
No, because they're moving.
Go, because it's equal.
Ah, yes. Right? So the zero, sum is zero. Well, negative 1 million and positive 1 million would also still equal zero.
It's like if something has like negative momentum, it would cancel out with the positive.
Yeah, so again, this is where we get into the physics of this and the actual math of this. And you'll see, we'll get through it today, where positive and negatives matter.
So if something's moving and then it explodes, it still cancel each other out.
Why you gotta make it so hard? Gosh. But yes, the key concept here, this is always, always, always true. We've never found a way in the world of physics to violate this particular thing. That's why we call it the law of conservation of momentum.
We should have a lab and try to figure out.
We should try it. We should just skip the rest of the school year and try to violate core laws of physics. Someday in your doctoral thesis in physics, I can't wait to see you succeed in breaking this particular law. You will be the talk of the town in the world of physics, that is for sure. So, all right, let's talk about quickly the two types of collisions.
It's the friction of them trying to hold together.
All right, let's debate physics later. What is this, physics class? Stop it. All right, so for the purpose of this class, we are going to generally define out two different kinds of collisions. Most of the examples I give are going to be one or the other of these types. What is the difference? We just talked about it a moment ago. Give me the non-book definitions of these two things. The quick and dirty definitions of these.
Elastic is bouncy and elastic is not. Or stretchy, bouncy. All the above.
And inelastic,
Doesn't bounce off. Sticks.
you can do better. Sticks. Now, this is only important in that I'm going to write questions and I'm going to say, given an elastic collision or given an inelastic collision or whatever, and that's just going to inform you on like what kind of collision we're talking about. Now, in the gizmo yesterday, that slider that you saw at the top, there's all different versions of this. This is a sliding scale. You can have a perfectly elastic collision. You can have a perfectly inelastic collision where they stick together. And you can actually have all the different versions in between. That has to do with kinetic energy, which we're not going to get into in the scope of this class, but I just don't want you to send me a harshly worded email in a couple of years when you're in physics in college and your college professor gets into this. And you're like, Clymer lied to me. Yes, I did.
How do you tell if it's elastic, inelastic? Is it like the material?
No, it has to do with the kinetic energy changes, right? And the kinetic energy and the energy loss, and it's messier than we need to get into for this class. But yes, you can tell. Based on the math, you can figure out, to your point, yes, you can solve that, but we're just not.
We're not going to have to figure it out ourselves.
You're going to not have to figure that out yourself. We're going to stick to the momentum side of this, but just know that all these things are related. And so in college, you don't have to, I mean, you can send me that strongly worded email. That's actually fine. You know. So let's do some math. I don't want to do this. So let's bash some objects into each other, shall we? All right, so in your notes, I don't know that you have to write this whole thing. But this is what a problem is going to look like in this class. So you can kind of summarize this or just write it out how it is. But let's start with this problem. And I'll scroll down in just a second so we can get the very end of this question. Two objects collide, just like we've had in the investigates for the last 2 days where you're bashing the blue carts together and colliding the blocks in the simulator. Now we've got a real problem to solve. Two objects collide. Object 1 moving to the right. It's 2 kilograms. They stick together. We're trying to figure out what happens when it's all said and done. Also not listed here is like it's on a frictionless track, and we're going to ignore air resistance and friction and all those sorts of things. We're back to ignoring friction. We spent all that time learning friction, and now we're just summarily ignoring it again. Dang it. Poor friction. Friction never really knows if it's going to be used or not, right? It's a sad day for friction. We're back to ignoring friction. Poor thing. All right, everybody got at least the skeleton of this kind of written out? All right, so let's figure out how to solve these problems. How are we going to solve these? Step 1.
Draw the equation.
What?
Draw it.
Do what?
Draw it.
Venn diagram, not Venn diagram. What's it called?
No, you're so far ahead, bro. No. Yes. Draw a picture is correct. In fact,
Yes.
we're going to like drawing one picture so much, we're going to actually draw 2 pictures.
Yeah. That's like English. Yeah, it is English. Diagram is a bad.
So this is how I am going to set up a collision problem. I'm going to have a before and an after. I'm going to start with a picture. And now, again, the physics to go and the gizmo all kind of led you to this point. I have 2 objects. So what's our before condition here? Yeah, so what's number 1 doing? What was the mass of object 1? What was its velocity? 3. And what was object 2 doing? Nothing. Just minding its own business. What's the mass of object 2? And what was its velocity then? What are we going to list here for velocity? 0. What is our after situation? This is all we know, right? This is all we really know about before. So what's after? Oh, we collided. Right? And the question told us they stuck together. What do we do with our mass now? Yeah, so now how many objects do we have? We kind of have 1 object. Yes, there's still 2, but they're stuck together. So for the purpose of their motion, what's going to be true about their velocity, the 2 blocks? Yeah, it's going to be the same. They're connected together. Right? So our mass now is going to be what? Yeah, 4.5. It's going to be Mass 1 plus mass 2 equals 4.5 kilograms. However you want to think of this. If you just want to write it down, obviously the math here is really pretty easy. Yes?
Is momentum M, or what would you?
No, it's not that easy.
Yeah,
Physics hates us. What letter do we use for momentum? Nope.
Kilograms times meters per second.
Well, that's the unit, but what letter do we use? This is in the reading. What's that? P.
What?
M was already taken.
Oh, yeah, that's
M was already taken. So I guess we just move through the alphabet until we find a free letter.
Second letter.
Okay, so you've got a lot of great suggestions that I don't disagree with, but unfortunately, some physicist at some point in time was like, let's use P. Okay, well, there it is. So we'll get that over here. All right, what's our velocity over here? I don't know is the right answer. That's not given. Right? Well, we're going to get to that. That's what we're trying to solve for, but for now we just don't know it. So let's go back to our before, because now we're kind of at,
Look at the due date.
we're at our end point here. There's nothing else we can, the question did not give us anything else
Mr. Mellon got it.
than this. So now what?
Mr. Mellon got it, that's right. Nothing I can do, like, get it
It
signed.
wouldn't move to the right, right?
Mr. Mellon got it.
Well, we'll see about that. We'll be able to figure that out, but you're right. Intuitively, what probably will this do? Move. I would guess that when they, and again, you did this in the Investigate yesterday. We saw this. We did this with the carts, with the magnets. What is this probably going to do, I guess? It's probably going to move, and it's probably going to move in what direction? Well, this is an inelastic collision, so we're stuck together. When these stick together, what direction will it probably keep moving? To the right, to the right. Would you guess it'll be faster or slower? Probably slower. Right? So let's see if we can actually come to terms with the exact numbers here. So what has tipped you off that you're probably going to have to use momentum to solve this problem?
Anything else we can do?
Sure, but like what about the question is going to say, hey, if I need to get out of my toolkit some physics thing to solve this problem, how do I know that's momentum? Well, sure, but it's a what kind of problem?
Collision.
It's a collision. This is your like keyword, like, oh, things are colliding. Two objects are hitting each other. Whether they're bouncing off or sticking, I'm going to know that I'm going to need probably momentum to solve this problem. So let's solve for momentum. What's our momentum for object 1? How do we solve that?
Multiply 2 times 6.
Yeah, so we just use our definition of momentum. It's mass times velocity. We can do that in our head. It's got a funky unit. There's no unit for momentum. Not like, kilograms or newtons or anything fancy. It's just kilogram meters per second. Again, they took all the time to pick like the worst possible letter for this. They probably could have made a unit, but could have done so many things, What's the momentum of object 2? 0. Okay, what is our total momentum before our collision? 6. How do you know?
Because you would add them.
Yeah, we just add them together. It's literally that simple. Our total momentum here is 6.0 kilogram meters per second. Okay, so how does that help us?
Now we know what the other.
Now we know what?
We know the other momentum.
We know the total momentum after. Right? Total momentum before is going to equal total sorry, it's low. Some of you may not be able to see that. P total. Total momentum. Well, this actually then is easier. Right? Because how many objects do we have on the right-hand side? How many objects do we have after this particular collision? Just one.
Now we can just use our equations.
Now we can just use our equations. P equals momentum. P equals momentum equals mass times velocity. So this is going to be 4.5 times v. And our velocity is going to equal and let's use our smell test. Does that answer look like it's possibly true? I feel okay about that answer? Sure. How am I going to make these problems more interesting?
We're going to make them collide and not stick.
Okay, I can change the type of collision. What else? Okay, I don't know that I'll do that. I don't know that I'll do that. I could, if you upset me greatly. Yes, I'll do that. Okay, now we could change the motion of some of them. What else could I do? Okay, could change the elasticity.
Friction.
No, I'm not going to add friction. You guys that's too savage even for me.
Not give you something.
What could I maybe not give you?
Anything.
Anything. Maybe I give you a velocity here and not a mass or whatever. I'm going to take one of these or two of these pieces away. You're going to have to basically do the same math, but you're going to have different holes in it somewhere. Right? So, I mean, you called it up. I suppose I should answer.
No. This was an invitation. Well,
In your notes, let's do another problem. Two objects again. I mean, I wouldn't be doing my job if I didn't do exactly what Charlotte wanted me to do. She claims she never asked, but
I didn't know what I was getting when the coach
Sure.
told me to take this class.
yeah.
I know, I didn't ask for
Mistakes were made. Mistakes were made. So two objects again.
What's it asking for?
Well, what's the result of this collision? So in this case, similar to the last problem, if it's inelastic again, now I didn't tell you exactly what kind of, or I didn't describe the collision, I just told you what kind it was. And my advice is to simply solve this the same way we did the last one, with the additional wrinkle of, obviously object 2 now is moving. It's no longer an innocent bystander.
Two different motions. Motions after or before? Well, actually, they're both. But, one. Wait.
Times
No, 3 times 6, 6. 4 times 4 is 16.
Kilogram meters per second is definitely the unit. That doesn't look right. What is this representing then?
No, you're being stupid.
the momentum, the speed left, actually. So would that be times?
You're on the right path. That's not the right number though.
How do you know that the before is not 16, the before 10?
The one object that both
It's total.
Debate team, you guys come up with an answer yet, or are you just gonna argue it out until you get there? Well, this is a momentum quantity.
It's 16 and negative.
Kilogram meters per second is momentum. So if you're multiplying those things to get this is a momentum quantity. If this is gone, then it's just meters per second. That would be a velocity. So, no, that's not right. Well, what happens at the end of this? Like if you were to describe to me what happens.
You don't want a number.
So these two things hit together, inelastic collision. So what does that mean? And then what is that thing doing?
Is that because like one would have to be negative, so then that, and then just that divided by that?
Well, yeah, but then you're going to have to, I guess you're kind of doing it with this, but I don't like that all of those numbers are positive. I feel like that feels bad, man. I feel like mathematically there's a way to represent left and right.
Climber, we have to leave.
You're close.
What? Oh, yeah.
So if I just make these negative then?
Well, I guess you'll just never know what happened to these two objects.
Where did we go after this? I found my phone.
All right, spoiler alert. If your total momentum for both sides is 22, you're not thinking about this exactly right. There's an additional wrinkle to this data that does not lead to the path of 22 kilogram meters per second for total momentum. Why?
Because this one.
Yes, yes, yes. Yes. So then how do we get over here and solve for this combined thing? Remember, this is, so what does inelastic mean? No. Yes. Yeah, if it was this, it's impossible to solve. There would be no way for you to do that. I didn't give you enough information to actually solve it that way. Yes, but I would have done, I would have made that negative, right? Right? Like if you, truly, like that's the math you did. You said, fine, if you got to 10, that means you made one of them negative.
You can keep it.
Yes, but now, yes. Yes. I mean, sure. You don't need it wherever you're going?
Well, I was just talking about 8 punch.
Oh, okay, yeah, sure. I'll hold it for you. I promise I won't do any of your homework. How about that?
So after we figure out.
I guess I bring myself.
It's complicated. I know. Plus all this is being recorded, so I have video evidence of you kidnapping students. I know, it's
Hey, I
bad.
just got one too, so I gotta hang mine up.
I already hung mine up.
Who gave it to you?
I can't tell you that. It's a secret. Oh, geez.
Sorry.
Anybody else want to just leave, I guess?
After we find a total momentum, can we do anything else or anything?
What's wrong?
We're going to talk about that in just a minute. All right, so before, you know what? I've already done this.
We don't.
Let's just validate that this is what this should look like.
Wait.
Now, what is the wrinkle here? What is the key difference here? What is the core concept that you have to kind of, what's the leap? Yes. One of these two things you must decide is negative. And this goes back to our definition as a vector quantity. Momentum, one of them is negative. Now, truly, you could pick left or right as negative. If you just want to watch the world burn, I guess you could pick right being negative. Fine. The math will work out in the end either way.
What do you get for velocity?
Negative 1.67. I'm not going to change the way I do physics because of a middle school meme. This, I can promise you. But yeah, so the big leap here is you have to consider one of these velocities is going to have to be negative. I picked left being negative. Just convention. And then let's just for a moment, before we end this, does this make sense?
Yeah.
Like if I have these two objects, which object is more massive, 1 or 2? 2. Which object is moving faster? 2. So when they collide and stick together, what direction should they probably be going afterward? Left. Whatever direction the bigger, faster, or more massive, faster thing was going. So that just feels right to me that my ultimate velocity is negative 1.67 meters per second.
Oh, wait, never mind.
Yeah, because once we get to here, right, then getting here is pretty trivial. It's just P equals mv. So again, we're not going to do a quiz tomorrow. I didn't get far enough along on this to really punish you guys enough to do a quiz tomorrow. We are going to do more problems like this, but now we're going to add the wrinkle of what if we have an elastic collision? What if they're both moving before and both moving after? How can we add a little bit of additional chaos to our collision? We're not going to do a logbook check because we're not quite done with this yet. So that's all getting kind of delayed. You have enough knowledge right now to do the physics to go. It's going to have to be done anyway, but I know assigning homework is sometimes a futile gesture.